Right, so we've introduced enough concepts, enough material, so that we can start talking about the dimension of a vector space. And that will lead us to introduce the idea of a vector space's basis. And that's got to be one of the most important concepts in all of linear algebra, not only in this course. What we've shown is that if you start with a linearly dependent set U, you can reduce that to a set of linearly independent vectors without changing the span of the sets, which is to say there might be fewer vectors in the spanning set. That's the finite number of vectors we use to build the linear combinations out of, but the span of those, the collection of all linear combinations, would be the same, even though our spanning set is now smaller, and it has the added advantage of actually being linearly independent. We've also shown that if we have a linearly independent set in a subspace W, and the span of that set is not the whole subspace of W, then you can make that into a larger linearly independent set U prime by adding some vector U which was not in the span of U to that set U. As an example, I have here a set with two vectors in R4, 1, 2, 1, 1, 1, 3, 5, 6. Two vectors, they are linearly independent. It's easy to see when there's only two vectors. You ask yourself, is one of them a scalar multiple of the other? The answer is no, not in this case. So they're linearly independent. I'd like you to find a bigger linearly independent set in R4 that actually contains these two vectors. So we need to find a vector that is not in the span of these two vectors, and then we can add that vector to the set that contains the two vectors, and we'll have a larger linearly independent set. Well, in order to find a vector which is not in their span, it'd be nice to be able to describe the span. So the span of these two vectors, here written as columns, would be all the linear combinations of 1, 2, 1, 1 and 1, 3, 5, 6. It would look like this. And I can simplify this a little bit by just multiplying the actual column by A, the other here column by B, and adding all the terms together. So I get that anything in the span of these two vectors is going to look like a vector whose first constituent is A plus B, the second constituent is 2A plus 3B, the third one is A plus 5B, and the fourth one is A plus 6B for any specific A and B in R. The thing is, once you've picked A and B in R, you have to use the same value for all the A's throughout, and the value of B for all the B's throughout. For instance, you could pick A is equal to 0 and B is equal to 0, and then you get 0 plus 0, twice 0 plus 3 times 0, 0 plus 5 times 0, and 0 plus 6 times 0. That's the 0 vector. Okay, well, so you want to find a vector V that has 4 components, which you cannot express this way. Like the 0 vector is not one such vector, as we said, because you can express it this way. Well, what about the vector 1, 0, 0, 0? If you could express it this way, if it was in the span of the two vectors, then you could write A plus B is equal to 1. So the first component here is equal to the first component here. 2A plus 3B is equal to 0. So the second component here is equal to the second component here. A plus 5B is equal to 0. Third and third. A plus 6B is equal to 0, right? Even though I wrote this here as a row vector, it's talking about the same types of things here. They're 4-dimensional vectors. So if we were able to write 1, 0, 0, 0 as a linear combination of 1, 2, 1, 1 and 1, 3, 5, 6, we should be able to solve this system. Well, from the last two equations, you get that A is equal to minus 5B, and you get that A is equal to minus 6B. So that automatically gives you that B is equal to 0. But if B is equal to 0, and here A is also A also has to be equal to 0, right? That's the only way this makes sense. But in the first equation, if b is equal to 0, you have a plus 0 is equal to 1, so a is equal to 1. So you'd have to have that a is equal to 0 and that a is equal to 1 simultaneously. That's impossible. But amongst other things, the second equation will also fail. So you cannot find a solution to this system, 4 equations and 2 unknowns, meaning that you cannot write the vector 1, 0, 0, 0 as a linear combination of these two. So that means, according to the theorem that we've seen previous section, that the set 1, 2, 1, 1, 1, 3, 5, 6, and 1, 0, 0, 0 is linearly independent. But it's not the only set where that's the case. Like you could replace the last vector 1, 0, 0, 0 by 2, 0, 0, 0. That's also not the only possibility. There are infinitely many different sets that are linearly independent that have 1, 2, 1, 1 and 1, 3, 5, 6 as two of the vectors. You can find sets with 3 vectors. You can even find sets with 4 vectors that are going to be linearly independent, but you cannot find sets with 5 vectors that would be linearly independent.